All right, now we'll talk about gases, and these are what we consider a gas is something that's a gas under normal conditions. So 25 degrees C, that's around normal room temperature, and 1 atmosphere is around a normal sort of atmospheric pressure. And we have the monotonic gases. So this is all of our noble gases that we have over here. All of these are gases. And then we have our diatomic gases, N2, O2, F2, Cl2. And again, hydrogen, for the purposes of this discussion, would be better placed right here. It's another diatomic gas. So if you think about moving hydrogen over here to the end of this spot, then all of those are clustered together. Another important triatomic gas is O2 can exist as O2, but it can also react and form O3, which is ozone. And we have a protective ozone layer around the planet. All right, first let's talk about a combined gas law problem. So we have a car cylinder engine that has a volume of 352 centimeters cubed. The engine takes in air at 21 degrees C with a pressure of 0.945 atmospheres. The compression stroke squeezes and heats the gas until the pressure in the cylinder is 4.95 atmospheres and the temperature is 95 degrees C. What's the final volume in the cylinder? So anytime we're changing any of the parts of the problem, so if we're changing the volume, which we clearly are, we have an initial and a final volume, we're changing the pressure or changing the temperature, we have to use the combined gas law, which is this one. I always suggest as a first step before you do any algebra to cross multiply this and then solve for whichever factor it is that you need. We've done that here, so we're solving for V2 in terms of all the other variables. And then just going into the problem and finding them. And again, the most important thing for this type of problem is to make sure that everything correlates together. So this volume correlates with this temperature and this pressure. Pressure can be in any units. Volume can be in any units. The temperature has to be in Kelvin. So we switch the temperatures over to Kelvin. We can leave the other as whatever units they are. And then whatever units we've left there is what will come out. So 84.1 centimeters cubed. Centimeter cube is actually the same as a milliliter. So 84.1 milliliters or 84.1 centimeters cubed. And so let's see if this makes sense. Pressure increases, volume goes down. So we're squeezing that gas down into a smaller volume. Therefore, the pressure is increasing. All right, and then we have the other gas law that we'll use. Anytime you see moles, it has to be this gas law because this gas law is the only one that has a capacity to handle moles. It has this N right here, which is moles. Pressure times volume is equal to the number of moles times the gas constant times the temperature in Kelvin. And so as soon as I see I'm doing something with moles of gas, it has to be this one. It can't be the other one. And also I'm not changing anything, so I have the moles, I have one temperature, one and only one temperature, one and only one pressure, and so I can plug in my pressure, my temperature, my number of moles, the gas constant, and solve for the volume. And I do that here. Those units cancel appropriately, and we're left here with a volume. All right, here's another example. So if you know all the variables except one, you always can rearrange to solve for that. And here, again, we're looking what volume will be occupied by 0.393 moles of nitrogen gas at 0.971 atmospheres and 24 degrees C. Solved for volume. Now we just put in the pieces, the moles, the value for R, the temperature in Kelvin, and finally the pressure, and we solve for the volume in liters. Okay, and this one will calculate the pressure in atmospheres exerted by 2.18 moles of hydrogen gas in a 5.32 liter tank at 15 degrees C. So now instead we're solving for the pressure. We just go into the problem and pick out the pieces that we need, making sure to convert the temperature into Kelvin and put it into the calculator, and there we get our pressure instead. All right, so I've said this as we went through, so if we have a fixed gas sample. So if we have constant number of moles of the gas, but we're heating, compressing, changing the volume. So if we're changing any of those, only this equation can deal with that because it has two pressures, two volumes, and two temperatures. So it has to be this version, which is called the combined gas law. If we're not doing anything to it, i.e. we're not heating it, expanding it, anything like that, then we're going to use PV equals nRT, and we're either going to be given or have a way to solve for these variables, put them in, and then after we put them in, solve for the missing variable. This can also get turned around. This equation can get transformed into an equation for the gas density, and once you've done that, the gas density is equal to the pressure times the molar mass of the gas divided by RT. All right, so here's our equation. The density of a liquid or solid is expressed in grams per milliliter, but for a gas, the density is so low that we use units of grams per liter. And now we can calculate the density of CO2 at STP. So we've got a few things to decode here. So we will need the molar mass, so we will need the periodic table to figure out the molar mass of CO2. And then we need to decode STP. So standard temperature is 273 Kelvin and standard pressure is 1 atmosphere. Here's the molar mass of CO2, here's standard pressure, here's standard temperature, and then there's our gas constant R. So the density of CO2 at STP is 1.96 grams per liter. All right, you'll also be able to be asked to do some problems like this where you're using gas stoichiometry. So for these, you're going to have to do a little bit more work for the N value that will go in. An airbag should be filled with gas at a pressure of 829 torr at a temperature of 22 degrees C. The bag has a volume of 45.5 liters. What amount of sodium azide should be used to generate the required amount of gas? So what we're going to do is solve for the N that we need, because we're given a pressure, a volume, R is a constant, and then we're given temperature, which needs to be converted to Kelvin. So we can figure out the number of moles of the N2 gas that we need. So once we've figured that out, we can convert back to the moles of the sodium azide and then finally the grams of the sodium azide. So after we've done this chapter 5 part, we go back and this is like a chapter 3 problem. 2.05 grams of N2 gas. We use the stoichiometric relationship 3 to 2. 3 moles of N2 comes from 2 moles of sodium azide. Now we've simply used the molar mass, which we've calculated from the periodic table, 1 sodium and 3 nitrogens, added their masses together to give us 64.99 grams of sodium azide to this in 1 mole of sodium azide. And now simply put this in the calculator and we find out that we need 88.8 grams of sodium azide in there in order to generate the amount of gas that would be required to fit what we need here. All right, another type of gas stoichiometry problem. What volume of H2 measured under these conditions can be released when 42.7 grams of zinc reacts with HCl? So this is a chemical reaction. We need a balanced chemical equation. Most importantly, we need ultimately to know that the relationship is 1 zinc to 2 HCl's. But it's good to go ahead and write the whole balanced chemical equation. All right, so we're given a mass of zinc. We use its molar mass to convert it into moles. We use the mole ratio of zinc to H2 to figure out how much H2 gas that we can make. So we're going to make this number of moles of H2 gas. And now it's simply, we use the ideal gas law. We're solving for the volume. We just calculated N. R is a constant. The temperature in Kelvin we get from the temperature in Celsius, and then the pressure here, we're going to need to convert that into atmospheres. 16.2 liters of H2 gas. All right, and then now having done a good part of the course, we have this mole map that we can use. So we can start with moles of one species. So this would typically be a reactant, and then B is a product, say. And starting with some number of moles of the reactant, we need the balanced chemical equation to figure out how many moles of the product we can make. If it's at STP and it's a gas, we make, there are 22.4 liters of gas per 1 mole of an ideal gas at STP. If it's not at STP, we have to use PV equals nRT to solve for the volume. If we were to simply go across this way, this is a chapter 3 problem. So a reactant forms a product, and then we convert it into the mass of the product that forms. And then to get to a chapter 4 type problem, a reactant reacts to form a product, and then maybe that product has some concentration in a solution. And so we have a molarity here, and we can convert to moles or liters of solution at the end. All right, and then finally, we should talk about gas mixtures and partial pressures. The mole fraction of a gas is the number of moles of a particular substance in a mixture divided by the total number of moles of all substances that are present. For a system of just 2 gases labeled A and B, it looks like this. The mole fraction is equal to the moles of gas A divided by the total number of moles of all the gases. And then the pressure, the partial pressure of A is equal to that mole fraction times the total pressure. B, it's the same type of equation. The mole fraction of B is B divided by the total. And in this 2-gas system, it's the same total. And so the partial pressure of B is equal to the mole fraction of B times the total pressure. And then all these also have to be true. The mole fraction of A plus B, there's only 2 gases, has to equal 1. Total pressure has to be equal to the partial pressure of the 2 gases. And then the total number of moles of gases has to be equal to the moles of gas A and the moles of gas B.